statistical tests, we can look at what we've covered so far and what we still need to do in this table. You can break up statistical tests by the type of independent and dependent variable that is involved. If your independent variable is categorical, in other words, a group, some certain groups, and the dependent variable is quantitative, so for example, weights, then you would want to do a t-test or ANOVA, depending on the number of groups that you have. So for example, we could explore whether the mean weights of the different treatment groups are the same. If the two independent and dependent variables are both categorical, so for example, we have counts for each of the different groups, then we would do a chi-squared test. And so, for example, you could ask whether the number of patients of different treatment groups is following a certain multinomial distribution. Today, we're going to cover the case where independent and dependent variables are quantitative. So, for example, your independent variable could be weight and your quantitative variable could be height. And you want to see whether you can predict height from weight. This is called linear regression. When the dependent variable is categorical and independent variable is quantitative, for example, we might want to predict whether a patient is going to get a disease based on their weight, then that is a type of regression called logistic regression, which is not covered in this class. So today what we're going to do is we're going to explore the matrix notation in multiple regression. We'll also introduce this simple standard regression model for K is 1 predictor, and do a geometric derivation of the regression coefficients. Okay, so a bunch of matrices here. We have Y is our response variable and the X's are our predictor variables. So we have n observations, and so we have these column vectors. We also have coefficients, beta 0 to beta k. So beta is a k plus 1 by 1 column vector. And we also have error terms, one for each observation. So that's a n by 1 column vector as well. Put all the x's together, x0 to xk, we get an n by k plus 1 matrix called the design matrix. N here is greater than or equal to k plus 1. We assume that x is full rank, which is to say that these column vectors are independent, so that x transpose x is an invertible k plus 1 by k plus 1 matrix. Now the standard statistical model is y is x beta plus e, where e is homoscedastic, meaning that the variance of the EIs don't depend on x. So we'll see what this means shortly. So these EIs are independent random variables with expectation 0 and variance sigma squared. We'll soon assume that they're normal, but that's not actually part of the standard statistical model. The xi's are assumed to be fixed. So here we are now. So the xi is your data, which is considered fixed. And so we have y is x beta plus e in matrix, in matrix notation here, which amounts to these n equations, one for each observation. So you're writing an observation. So basically, this is going to allow you to predict a response based on your fixed predictor values. So in the case of simple, the standard statistical model, when k is 1 and let's say 3 observations, let's assume that there's a linear relationship between x is father's height and y son's height, given by our model here. Y is beta 0 plus beta 1 x plus e. So here I've drawn for you the scatter plot of these 3 points, xi, yi pairs, and we have 2 lines. One is the best fitting line through your data, which is called the regression line, and then the other is the Tyche line, which is the true relationship between the x and y that's given by the statistical model. So y is beta 0 plus beta 1 x plus e. Now we don't know what beta 0 and beta 1 are, nor do we know what e is, obviously then. So I've sort of drawn it in a picture for you. The distance from our scatter plot points to the Tyche line is E1, E2, E3 as shown in orange, and the distance to the regression line, those are called residuals, and those are in purple. So we wish to find the best fitting line through our data that minimize the sum of square residuals. So now, since these EIs are homoscedastic, the residuals should also be approximately homoscedastic. In other words, the residuals, the spacing of the residuals around the regression line should be fairly constant and essentially hugging your regression line. So who is Tyche? Well, Tyche is the goddess of fortune, and only Tyche knows what beta 0 and beta 1 are. Now, there is a modern day Tyche who lives in Sin City. This is the other Tyche, and you can find her on the internet if you like, and you can hold an image of either Tyche, whichever suits you. But the important thing here is that the Tyche line is only known to Tyche, and all that we see is the data, and hence we can form a regression line, but we'll never know what the true Tyche line is. Our regression line is the best that we can do to predict son's heights from father's heights. So now you should always plot the residuals. So this is called a residual plot. And so the picture on the left is a good homoscedastic residual plot. The picture on the right is a bad heteroscedastic residual plot. So in the picture on the right, the variance of the residuals is changing with x. This is not the case on the left. So we want to minimize the square root of the sum of squares of the residuals, or in other words, the Euclidean norm of the residuals. And what is the Euclidean norm? The Euclidean norm of a vector is the square root of the dot product of the vector with itself. So if x is x1, x2, then the Euclidean norm is essentially the distance. So the Euclidean norm is the distance from the origin to x1, x2. In other words, the square of the Euclidean norm is the sum of squares of the xi. Now there are 2 ways to find our coefficients, beta hat. One is using calculus, method of least squares. We want to find the best fitting line through our scatter plot. In other words, we want to find beta 0, beta 1 hat, beta up to beta k hat that minimizes the Euclidean norm of the residuals. there's that way, but then there's also the geometric way to do it, which is not covered in the book, but I'm going to cover it here because it's a very simple picture, and it covers both the simple regression and multiple linear regression cases. So we have a vector y, which is our response variable, and the columns of x span a k plus 1 dimensional subspace of Rn, since x has full rank. So I've drawn a picture here where y is sticking out of the column space of the x's, because in this picture n is strictly greater than k plus 1. Now, beta hat is, we want to find beta hat such that the distance from y to the column space is as small as possible. So what beta hat would we choose? Well, we would just drop an orthogonal projection from y onto the column space, and the distance from the origin to that point on the column space is going to be a linear combination of vectors, of column vectors, and that particular linear combination will give us our betas. So that's the plan here. So so in this picture here, you can see I've dropped an orthogonal projection, and here x beta hat is a particular linear combination of x0, x1, xk, and the vector from that point on the end of the arrow of y hat to y, that is the vector shown here in orange. This is the residual, and it is as small as possible. So what this is saying is that the dot product of the transpose of x with the residual is 0, and so what that means here is that I can just use my distributive property of matrix multiplication here, and we get x prime, the x transpose y minus x transpose x beta hat is 0, and you can solve this for beta hat using so you can solve this for beta hat, and you get the beta hat is x transpose x inverse x transpose y. And again, x transpose x inverse exists since x has full rank. So now that solves the problem. In the case when n is equal to k plus 1, this is a very, very simple case. So then y lies in the column space of x, and so the distance from y to the column space of x is 0, because y lies in the column space. And remember, y minus x beta hat is the projection onto the column space. And so what that says is that y is equal to y hat. In other words, our data is lying on a straight line exactly. So the data is actually lying on the residual, the regression line, and there are no residuals.